non-human derived, more natural systems. I'd now like to welcome Dr. Peter Breen. Peter, I've known for a long time.
Way too long.
And we enjoy a healthy tete-a-tete whenever we meet. He is a wetland guru without question, and I've looked up to him for a long period of time. So please welcome Peter Breen.
Thank you. So we're going to talk about wetlands, but just by way of introduction, we're mostly designers and practitioners, really advocates of any particular treatment system. But here we'll be talking about modifications to essentially runoff treatment wetlands for the wet-dry tropics. But to start with, really need to emphasise that no one solution treatment device is going to do the job we're talking about here. And really we're talking about a whole of catchment approach, a whole of approach where we're looking at land, water, the chemicals. We're just really talking about, in this presentation, this little piece here of treating some of those rural runoff issues. And as others, Tom mentioned as well, wetlands are not going to do the trick, and we really think there needs to be a treatment train approach, really starting from at source on the farm. Now, whether the treatment or the use of a wetland is on the farm or off farm kind of doesn't matter to that extent, but the starting points are really farm practices, and there's a whole range of devices here that could be used, buffer strips and so on. So this goes right back to, if we talk about cane farms, goes right back to the headlands, the tracks between the plots. Simply, are they grassed and managed as stabilised systems, or are they just left as muddy tracks and wheel ruts that, channelise flow? So right back to that kind of level is where you've got to start. We're just emphasising the treatment train. But one of the things that having this treatment train approach can do is, if you are deploying wetlands somewhere in that treatment train, the more pre-treatment you do, the potentially smaller the size that wetland can be, because you're reducing the loads as you're going. Having a treatment train approach is really crucial. And whether that's the whole farm setting, whether it's, in particular treatment device, management of the farm, or whether it's the farm runoff, all of those things have got to be tackled to be able to address the ultimate loads that are going to hit the reef. So if we start now talking about constructed wetlands, we've had a good introduction. They're densely vegetated systems, and the pollutant removal processes are complex, but largely they're plant uptake, filtration, enhanced sedimentation, and a lot of that work that is done by the actual biofilms on the outside of the plants. The plants are like a framework for a whole range of complex biofilms on the outside of the plants. So the plants are crucial, but also their epiphytes are particularly crucial. There was a question here about wetlands and how they might differ. We particularly advocate a kind of treatment train approach that's been introduced by Tom as well, where you have an inlet zone that's primary sediment device. Water flows through the system. If we look at it here, water flows into the sediment zone, flows through the macrophyte zone, and typically we would design a wetland with some kind of extended detention. So that is, the system is filling during an event, and when the runoff event finishes, it slowly drains out. Importantly, having a sediment zone allows you to bypass high flows. And really, I think any catchment runoff kind of approach where you're going to construct a wetland rather than restore floodplain wetlands, it's crucial to have that high flow bypass. You don't want the really big storms routing through your wetland, either creating damage to the vegetation or worse, erosion and transport of some of those trapped solids out during the runoff event. In terms of constructed wetlands, that's a real feature that needs to be considered in any designs. And so we just see that again, increasing extended detention. So treatment effectiveness been touched on a bit as well. What we do know from constructed stormwater wetland technology is when they've been monitored, event monitored, these systems do work and have worked in a whole range of different climatic conditions. Typical targets we try and achieve, and these are partly based on, these are a kind of best practice break-even points in the size of the wetland compared to the load reduction. And typically we're talking about 80% reduction in suspended solids, 60 TP and 50 TN. And a lot of those pollutants can be particulate bound. And so what we would find, and small amount of monitoring that has been done for things like other chemicals like pesticides and so on, is that any of the polar chemicals, things that adsorb to particulates, will be removed in roughly the same proportion as the suspended solids removal. But polar chemicals, things that are non-charged, can move through all sorts of systems. They'll move through biofilters, which are even more efficient at removing chemicals than wetlands even. So it depends on the particular chemicals. So what we have here is a curve prepared for wet tropics kind of climatic region, where we can see the treatment performance as a percentage of catchment area. And you can see sort of to get somewhere around 50% or so, or to get the kind of targets we're talking about, you're needing somewhere between 10 to 15% of the catchment area if you're going to rely solely on wetlands. And so we're starting to talk about the big numbers that Tom was saying would be a bit of an issue. So again, if we're targeting partial treatment by wetlands, you can get sort of 50 or so % of the job done. You still need 10% or so of the catchment. So it really does point to a whole of farm approach to requiring good protection of the reef. What we've tried to do is develop some water level modifications based on wet-dry tropics rainfall. So you're all familiar with the kind of rainfall patterns that occur in these areas with very, very dry winters and wet summers. What we've done is simply model some wetlands in music, but stepped up the permanent pool volume until we got an adequate dry out period. And so we've undertaken that assessment for a whole range of locations here, from Darwin to Townsville's probably the most difficult climate in Queensland to design for in terms of the length of the dry season. What we did with this was try and arrive at how long could a wetland that's dominated by large perennial emergent macrophytes dry out for. How deep would we have to make the permanent pool to allow a satisfactory dry out period that those plants could survive? How deep was that, and would that compromise that particular vegetation community? And how deep would we have to make some permanent pools in those wetlands to provide refugia for things like predators, mosquito predators and so on. We undertook that modelling and used continuous time series. We then analysed the water level variation outputs from the model to look at how long those dry periods would be, or how deep we had to make the permanent pool to achieve our target dry out period. And the idea of the target dry out period is to preserve the large perennial macrophytes in these constructed wetlands. And the target there, the reason for that is you want to have a system that is ready to function at the start of the wet. And so once that system starts to fill, the biofilms start to grow, the plants start to regrow, and you've got an operating system ready for that first flush coming out of these dry season catchments at the start of the wet. So that's quite important. If you used some of the natural wet-dry tropics and wetland models, they're not satisfactory for construction, for treatment of runoff in this way, in that you get wet season grasses growing in those natural systems. They dry down, decay, you get a dry season grass coming up, they get flooded, that decays. And so really designing for perennial wetland vegetation is the key in this sense, I think. For our modelling, we chose a dry period of around about 2 months, 60, 70 days. That's when the water level hits zero. So you have another month or so of dry out of the sediments, and then a survival period of 30, 40 days, which most of these large emergent plants can cope with. It's the dry period is also interesting in terms of the sediment chemistry, because regular wetting and drying, the same as in rice soils, causes the phosphorus that's adsorbed to iron particulates to be progressively more and more occluded into those iron oxide particulates. So on re-wetting, not so much is released. Soils that are regularly wet and dried, like rice soils, you've got to just keep pouring on the phosphorus fertilisers, because even though there's phosphorus in those soils, it doesn't become available on re-wetting. So the drying's quite an important element to the overall picture. This is some of the results for, I think, Townsville, where we had to crank up the permanent pool volume to 800 millimetres. Now, if this was a steady state kind of condition, that's way too deep for many emergent macrophytes to cope with on a permanent basis. But as you'll see from the water level variation analyses, that 800 mils is only achieved for a very short period of time. So this is inundation frequency curve with percentage of time along the bottom, and water depth on the axis here. And the permanent pool normal water level here set at 800 mils. You can see only 10% of the time is the water level at full level. These plants like around 300 or 400 mils of inundation, and you can see that's achieved. The pivot point, if you like, in the point is achieved around 50% of the time. Even though we've got a deep permanent pool, designed permanent pool, that would inhibit lots of macrophytes, it's only there for a short period of time. And in the dry tropics, it only dries out for 25% of the time, which is a little bit longer than the 70 or so days that we've identified. What we see here is similar to Tom shown, permanent pools of 2 metres or so, and with that kind of modelling approach you can tailor a wetland design to cope with most wet-dry tropic climates. As we're shown here, all from Townsville, which is difficult, to a range of other places into the wet tropics. So permanent pools range from 600 to 800 or so millimetres in depth. As you get to really difficult places like Townsville, your plant selection may vary, but here's Phragmites that can cope with a huge amount of water level variation and really quite dry conditions and still survive. Quickly cover one case study, which is a banana farm in Innisfail, Cairns kind of area, run off from a whole range of conditions, but 2 catchments, one major catchment that we were able to pretty much wholly treat, and a subsequent catchment that just was put through some riparian zone areas. Retrofits always opportunistic and never completely the desired area. This just shows the riparian zone area. A pool is going to be created here and route flows through this riparian zone. The other catchment was fully captured through drainage to the river. They had this just on-farm drain. A sedimentation basin was created on line, and that was used to sidecast flows into a treatment wetlands and some areas and so on here. Essentially that picture was this sidecasting sedimentation basin, flow through the wetland and returned. The river was down here. This is an important feature I mentioned earlier in the talk about allowing a bypass. So not all the high flows get routed through here. Once this system is full and diverting a set amount of flow in here, controlled by a pipe, the system just fills and spills. So the wetlands protected. This is the system being constructed. Here it is after construction, which is not ideal. So this is constructed by the farmer and really not adequately planted. Whenever kind of systems are employed on farm, there really needs to be enough funding and assistance to get good planting. Sizing's right, edge zones not very well planted, erosion. Whenever these kind of programs are initiated, you know, there needs to be some follow through and understanding of really how much it does cost. That's what it could and should look like, a different system that's been vegetated. I'll stop.